Hello, today we're going to cover a new method called the variation of parameters. And this method is used when the non-homogeneous term is not nice. And remember, our definition of nice was that if we take our function and find derivatives of it over many derivatives, it either goes away or it repeats itself. And so we're talking about not nice, things like the natural log of x or tangent of x, or really anything that's not exponential, polynomial, or sine cosine. Okay. Now, the cool thing is that in this particular method, we can use the variation of parameters even if g of x, the non-homogeneous term, is nice. So variation of parameters works for any g of x that we have to deal with, unless it's zero. So the method of variations will also work for higher order differential equations, just as the method of undetermined coefficients did. However, we're only going to focus on second order differential equations. That is all that you are required to know about. Your book does go over the derivation of higher order, and it's a bit intense. It's just a lot of labor to get through problems in those. So we want to focus on what we need to know just for second order. So the very first step that we're going to take is we're going to put our linear differential equation into standard form. Remember, standard form means that the highest order derivative in your equation has nothing next to it, right? We don't have anything for a coefficient other than the invisible 1, all right? So if there is something next to, in this case, y double prime, then we need to divide all the terms by that coefficient. Once we've done that, then our linear differential equation will be in standard form. We say that the coefficient in front of y prime is p of x, and the coefficient of y is q of x, and on the right-hand side, that's going to be f of x. What we call these names doesn't really matter a whole lot. It's their placement, okay? So the first thing we'll have to do is the same as we did with the method of undetermined coefficients. We will solve the associated homogeneous part using the processes that we learned in the previous sections. Once we've identified our two solutions, because we're working with second order, we should expect two solutions, we will write up the complementary solution and then make sure we don't forget about it, all right? And then we'll work on finding our particular solution. So the key to the variation of parameters is that we are going to make an assumption that our particular solution is a linear combination of the complementary solution, where the coefficients of the y1 and y2 that we found when we found the homogeneous solution or the associated homogeneous complementary solution, the y1 and the y2 that are here for the particular solution are the same y1 and y2 that we solve for. The u1 and the u2 are things that we do not know. Okay, so y1 and y2, those are coming from y sub c. Okay, so when we write up our complementary solution, be sure that you're clear on which one is y1 and which one is y2, and don't let them switch places. Like, have it set in stone. y1 is this one, y2 is that one, and then you're going to work with them with those names, okay? The u1 and the u2, this is what we try to find using the variation of parameters. Okay, so if we were to, your book goes into a lot of detail about how they come up with this system of equations, but really we're taking derivatives and second derivatives on y sub p, the particular solution, and there's a bit of algebra that goes on there. Then what ends up happening, though, is we end up with a system of equations. y1 u1 prime plus y2 u2 prime will equal 0. And then the second part will be y1 prime u1 prime plus y2 prime u2 prime is equal to f of x. Now, y1, y2, y1 prime, and y2 prime, those will be known because those are based on what we got in the complementary solution. What we're trying to find when we solve this system is we do not know what u1 prime is in these spots here, okay? Now there are some rules, some things that we learned way back when, and maybe we didn't learn them in college algebra, about how to solve systems of equations, okay? We could use a process of elimination or a process of substitution, but ultimately there's a nice shortcut way that we can use every single time that will work, and it will allow us to find u1 prime and u2 prime without having to make a decision on what method will work best for me to solve for these things this time, okay? The rule is called Cramer's rule, and I've written up what it is. Cramer's rule is saying that u1 prime will be equal to w1 over w. Now, the w1 over w, these things are actually determinants, and we can see what they are down below here, okay? The w is taking the determinant where the first row of the 2 by 2 determinant is the y1 and the y2 solutions that we got from our complementary solution. The second row is their derivatives, their first derivatives. W1 says change the first column so that it's a 0 and the non-homogeneous term. The second column will remain y2 and y2 prime, okay? Then a shorthand way to look at this is just calculate w, and then we create this fraction where the result of the determinant w is in the denominator, and in the numerator we have a minus y2 times f of x. But I want to show you how if we were to calculate the determinant for w1, we do those diagonal products, and we get this is equal to 0 minus y2 times f of x. So that numerator, minus y2 times f of x, is actually still just the determinant, w1, okay? Similarly, if we want to find u2 prime, then we're going to be looking at this w2 over w, and w2 is down here. It's a 2 by 2 determinant where since it's w2, we change the second column so that it's 0 and then the non-homogeneous term. When we calculate the determinant on this, we look at those diagonal products, we get y1 times f of x minus 0, which is exactly what we have in the numerator in the more simplified form, okay? So you decide how you want to do this, but ultimately they're the same thing. I'm not really saving any time either way, okay? Once we get these representations of u1 prime and u2 prime, they will both be functions of x, which means that we could find u1 and u2 by integrating with respect to x. And then once we know u1 and u2, we can take them and go back up to step 3 where we stated that y sub p is a linear combination of y1 and y2 with coefficients u1 and u2. We pop those in there and we have our particular solution. Now, remember that when we compute the particular solution, we do not put in constants of integration like we would for the complementary solution, okay? We're not going to put in another c or anything like that. When we use variation of parameters, we get the particular solution with nothing unknown. The c's are only in the complementary solution, so that's y sub c, the c1 y1 plus c2 y2. u1 y1 plus u2 y2, that's y sub p with no unknowns. If we have initial conditions, we apply them to the general solution, not just the complementary solution by itself, but the full-blown general solution, okay? I think this next paragraph I already talked about. We don't have to necessarily compute W1 and W2. We can use the alternate form, but it amounts to the same thing. And then at the end of the chapter, or the end of the section in the book, they talk about being able to do this for bigger or higher order differential equations. It just ends up giving us bigger determinants and more solutions to solve for. It becomes a bit more tedious. If you're interested in seeing how this applies to higher order differential equations, by all means go through that, but it's pretty analogous to what we're doing here for 2x2. So let's get right to some examples, because that's the best way to see how this process will work and make sure we're all understanding what the steps are. So in this example, we're asked to solve each differential equation by variation of parameters. Okay, so the first thing first is to note, is this in standard form? And it is, and that's good. So that means I can move on to the next step. The next step is find y sub c. So when we find y sub c, that means we're going to solve y double prime plus y equals 0 by letting y equal e to the mx, just as we did before in 4.3. So when we let y equal e to the mx and we substitute it and its derivatives in, we get m squared e to the mx plus e to the mx is equal to 0. Factor out the e to the mx, that leaves behind m squared plus 1 is equal to 0. M squared plus 1 does not factor at all. The e to the mx is not equal to 0 ever. And so I'm simply solving m squared plus 1 equals 0, which means m squared is negative 1. And that means I get plus or minus I for my solutions. So my y sub c will be c1 cosine of x, because my beta is equal to 1, plus c2 sine of x. I do not have an e to the mx or alpha x, because my alpha is equal to 0. So this is the simplest form for my complementary solution. I am going to denote the cosine of x to be my y1 and the sine of x to be my y2, so that I have that very clear for myself. All right, now I put a box around this and get to work with my particular solution. So now we want to find y sub p, which is equal to u1 times y1, which is cosine of x, plus u2 times y2, which is sine of x. Okay, I have to calculate all those determinants first. W will equal the determinant where the first row is y1 and y2, so cosine of x and sine of x. Then I just take derivatives. The derivative of cosine is minus sine of x. Derivative of sine is cosine of x. I take my derivative and I do that diagonal product, so I get cosine squared of x minus a negative, that'll be plus sine squared of x. And that is a Pythagorean identity that's equal to 1. Okay? Next, I will find W1. W1, that 1 tells me change the first column. So my first column will now be 0 with the tangent of x, since that's our g of x. My second column remains the same as it was in W, sine of x, and then the derivative of sine of x, which is cosine of x. When I take my determinant, this gives me back 0 minus sine of x, tangent of x. Okay, I can rewrite that if I need to, but I'm going to worry about it in a little bit when I have to integrate. I'll just go ahead and leave it this way for now. W2, the 2 tells me to change the second column. The first column remains as it was in W, so it's cosine of x, and then the derivative of that, minus sine of x. But now the second column is 0 with tangent of x. I calculate my determinants, that diagonal product. I get this is equal to cosine of x, tangent of x, minus 0. But cosine times tangent actually simplifies right down to sine of x. So I'm going to go ahead and simplify that. All right. Next, set up u1 prime and u2 prime. u1 prime is going to equal w1 over w2. Or sorry, not w2, over w. Okay, w1 is minus sine of x tangent of x all over w, which is 1. Now, tangent is sine over cosine. So the way I could rewrite this is to be a minus sine squared of x over cosine of x. And see if that helps me at all when I have to deal with my integration. Okay. The next thing is u2 prime. u2 prime is w2 over w, which is just going to be sine of x. I don't know why I wrote it that way. Sine of x all over 1. And that's just sine of x. Okay. Next, we're going to integrate. So u1 is going to be the integral of u1 prime dx. So I go ahead and plug things in. I have a minus sine squared of x over the cosine of x dx. And I'm trying to figure out what method I can use to integrate this. Now, the first thing that I can see is that maybe a u sub would work. When I have a fraction, u needs to be the denominator, and then du would be on the top. But if u is cosine, du would be minus sine. And I have an extra sign in there, so that doesn't work out very well. But maybe I could use a Pythagorean identity on minus sine squared of x. I know that sine squared of x is 1 minus cosine squared of x. So a negative sine squared of x would be cosine squared of x minus 1 over cosine of x dx. And then I could split up the fractions and see how things simplify. This becomes just a cosine of x minus 1 over cosine of x dx. Well, 1 over cosine of x is just secant, so I think this is going to work for me. I get the integral of cosine of x minus secant of x dx. All right, that'll work. The secant one. So for me personally, I put the integral of secant on the formula sheet for everybody because it's a trick to remember it, and I don't really like tricks. It's not even like a technique of integration. It's literally remembering a trick. And so I just give it to you, okay? If you're in somebody else's class, you want to ask them what they do, okay? The antiderivative of cosine is going to be sine of x minus the antiderivative of secant is the natural log of the absolute value of secant of x plus tangent of x. Okay. So that's u1. I'm going to highlight all that so I don't lose it. And then we're going to go on to u2. u2 will be the integral of u2 prime dx, which just means we're integrating sine of x dx, which will be a negative cosine of x. And that's it. Okay, remember we're not putting in the plus c's in here because they're not necessary for our problem. Of course, I do know that u1 and u2 is just general functions that we integrated to get would technically have a constant of integration, but it's not necessary for our purposes. So now we put everything together. We've got this minus cosine for u2, and now we can form y sub p and the general solution. So y sub p is equal to u1 y1 plus u2 y2. y1 was cosine, y2 was sine. So I'm going to put this in this way. So I have my y1 is cosine of x, and then that's going to be times my u1, which is sine of x, minus ln of the absolute value of secant of x plus tangent of x, close up parenthesis, and then plus y2 was sine of x, times u2, which is a negative cosine, so we have a minus actually, cosine of x. Okay, you should simplify this. If things combine, you should combine them, okay? What I'm noticing is that when the cosine distributes across the sum, I have a cosine sine, and then I have a minus sine cosine. Those are the same thing, okay? So in the end, my y sub p is just negative cosine of x times natural log of the absolute value of secant of x plus tangent of x. And that's it. It's almost a little disappointing that a couple of the pieces just went away, but sometimes that happens and it is okay. And the reason I stress it is because if you're practicing problems and you've got extra terms in there and you haven't let things go away, your answer will not look like what the final answer is. And so it's just, you need to be in the habit of completing all the algebra, combining all the terms before you say you're done. Our general solution, y, will be y sub c plus y sub p. Y sub c is c1 cosine of x plus c2 sine of x. And then our y sub p gives us minus cosine of x times the natural log of the absolute value of secant of x plus tangent of x. And then we're done. That's our general solution. Okay. All right, let's try one more. In this next one, we have y double prime plus y prime, plus 3y prime plus 2y is equal to sine of e to the x. So we've dealt with sine of x, and that was fine to use the method of undetermined coefficients. The reason why this one is not fine is that it's sine of e to the x. The derivative, first derivative would be e to the x cosine of e to the x, and the second derivative would be horrible. It'd be a product rule with a chain rule inside of it too. So variation of parameters is really the only way to go for this problem. So we go, I notice that my first term, it stands alone. So this is in standard form, which is good. And now I can find my y sub c. Okay, so we're going to solve y double prime plus 3y prime plus 2y equals 0 by letting y equal e to the mx and substituting it and its derivatives into the associated homogeneous equation. So when we do that, we get m squared e to the mx plus 3m e to the mx plus 2e to the mx is equal to 0. Factor out e to the mx. That leaves behind the m squared plus 3m plus 2. That's equal to 0. E to the mx is never equal to 0. M squared plus 3m plus 2 does factor, so we are now solving m plus 2 times m plus 1 equals 0. Therefore, m is minus 2 and m is minus 1. So then our complementary solution is c1 e to the minus 2x plus c2 e to the minus x. And I'll highlight that so I don't forget about it. I am declaring that e to the minus 2x is y1 and e to the minus x is y2. All right. And I'll box this off so that it's kept safe from all the other work we're going to do. All right. Now we want to find y sub p, which is u1, y1, and y1's e to the minus 2x, plus u2, y2, which is e to the minus x. Okay. First, we need to find our determinants. W is the determinant where the first row is e to the minus 2x, e to the minus x. It's just y1 and y2. take their first derivatives. We get minus 2e to the minus 2x, and then minus e to the minus x. When we calculate the determinant, we're doing that cross product thing, we get a minus e. Okay, when I multiply an e to the minus 2x with an e to the minus x, the exponents add, so I get a negative 3x. Minus the negative, so it'll be plus 2e to the minus 3x. I combine those and get one positive e to the minus 3x. Okay, W1 will be a determinant where we change the first column to be 0 and sine of e to the x. The second column remains the same as it was in W, which is e to the minus x and its derivative, minus e to the minus x. When I take my determinant, I get 0 minus e to the minus x times sine of e to the x. Okay, W2. With W2, the first column remains as it was in W, so it's e to the minus 2x and minus 2e to the minus 2x, whereas the second column gets changed to 0 and sine of e to the x. Calculate that cross product there, and we get e to the minus 2x sine of e to the x minus 0. And that's really all we can do. All right, so we have our determinants. Now we can form u1 prime and u2 prime. So u1 prime is w1 over w. w1 was negative e to the minus x sine of e to the x over e to the minus 3x, which when I bring that e to the minus 3x upstairs, it becomes a positive, and when it multiplies to the e to the minus x, I end up with a negative e to the 2x sine of e to the x. u2 prime is going to be w2 over w. w2 is e to the minus 2x sine of e to the x, all over w, which is e to the minus 3x. When I bring the e to the minus 3x upstairs, it combines with the e to the minus 2x to just be e to the x sine of e to the x. Okay, so now we have our u1 prime, we have our u2 prime. We can now integrate to get u1, my 1 is having a hard time, and u2. All right, so u1 will be the integral of u1 prime dx. So we're looking at the integral of a negative e to the 2x sine of e to the x dx. All right, this is going to be a u sub. And in that u sub, it's a little strange, but I'll just go ahead and do it and you'll see. So we're going to let u equal, you know what, I'm going to use w because, oh boy, I've got all these letters around here. Focus on, let's just leave it u and focus on this is a u sub, okay? We're going to let u equal e to the x because that's kind of the problem part inside of the sine of x. And then du will be e to the x dx. Okay, so this is kind of like my side work that's going on here. On the other side, when I substitute all of this in, notice that e to the 2x is e to the x all squared. And so I can actually like rewrite this to do what I need it to do, okay? Because e to the x all squared is just e to the x times e to the x, right? So let's see what that looks like. We get the integral of a negative. All right, one of those e to the x's outside of the sign is part of the du, because du is e to the x dx. The other one is a u, okay? And then we have sine of u and a du. Okay, So that fixed some things, but it introduced some more problems. This is still another U substitution, but I'm already using U. So now we're going to do a W sub. That's kind of why I went back to the U sub notation. So with a W sub, we're going to let W equal U, and then dW equals du. No, sorry, that's not what I want to do. It's not a U sub that works. This is an integration by parts. Goodness. Okay, so I have an integration by parts. I'm going to have W and dV, for lack of better letters. W will be U. dV will be sine of U. du. Okay. dW will be du, and V will be negative cosine of U. Okay, now we can go forward. UV or WV, and I remember I have this minus sign out here, so I'm going to put that minus sign totally to the outside. I'm going to put some brackets in, and I'll distribute it in a little bit, okay? My integration by parts tells me the WV, that'll be a minus U cosine of U, minus a negative, so it'll be plus the integral of cosine of U du. Okay, and now this further integrates. The minus sign will also go through, but we'll focus on this is going to give me U cosine of U when the negative goes through. The negative goes through to the other one as well, and the antiderivative of cosine is just positive sign, but with that negative sign, I get a minus sine of U. But remember, U is e to the x, and so this is e to the x cosine of e to the x minus sine of e to the x. That's U1. So let's go ahead and highlight that and move on to U2. I promise U2 is a little bit easier. Okay, U2 is the integral of U2 prime dx. U2 prime was e to the x sine of e to the x, so I'm just looking at the integral of e to the x sine of e to the x dx. This one is a U sub as well. We're going to let U equal e to the x, and then du will be e to the x dx. So the du is going to take care of that extra e to the x outside of the sine. And so then this just becomes the integral of sine of U du, which is a negative cosine of U. And when we put back in the e to the x, we get negative cosine of e to the x. That is my U2. Okay, next step, we're going to build y sub p and form the general solution. All right, so y sub p was equal to u1, y1, and y1 was e to the minus 2x, plus u2, y2, where y2 was e to the minus x. So substituting in what we found, we have an e to the minus 2x for the y1 times e to the x cosine of e to the x minus sine of e to the x for the u1, plus e to the minus x times the negative cosine of e to the x that's coming from the u2. We distribute. This is going to give me, when I take care of adding up the exponents for the exponentials, I get e to the minus x cosine of e to the x minus e to the minus 2x sine of e to the x, and then minus e to the minus x cosine of e to the x. And two terms go away. I want to just real quick make a point that it is merely coincidental that this happened with both examples that I'm working out. We don't always have terms that end up just adding away. It's just a coincidence. So those e to the minus x's with the cosine of e to the x's, those go away, and we are left with y sub p is negative e to the minus 2x sine of e to the x. And then we can form the general solution, y, which is y sub c plus y sub p. That's going to be c1 e to the minus 2x plus c2 e to the minus x plus y sub p, which is minus e to the minus 2x sine of e to the x. And that is our final solution. And that's all I have for variation of parameters. The process is the same every time. The difficulties come with the integrations. And so that may be where you need to put some of your focus, is on working on the integrations for U1 and U2 and really refreshing your memory and expanding your skills on integrating some more complicated functions. If you have any questions, please reach out.